Evening all, and welcome to our Chemistry Paper 2 live stream. So tonight what we're going to do is go through all of the work from C4, C5 and C6. Since there's a fair amount of additional triple science content, then what I've done is I've split it tonight so that those of you just doing combined science, you only need to be here for the first section, and I'll tell you when you're done. That means you can then mosey on off to do your own revision, and then those of you just doing the GCSE chemistry can stay and we'll do the separate science bit at the end because it's quite separate, so it works quite nicely. As always, we've got the chat window in the bottom there, so if you do have any particular questions that you would like me to go through, post them up. We are going to cover everything anyway, so that should cover all questions beforehand. But if I miss anything out, stick it in there and I will get to there at some point before the end. So, start us off then, C4, which was looking at these different groups. So the first group, which is group 1, quite conveniently, is known as the alkali metals. So the key thing we need to know about our alkali metals is that they are very reactive. So they're going to react with oxygen and water that we find within the air. So in order to actually prevent them reacting with the oxygen and water in the air, we store them in jars that contain oil. They do have typical properties of metals. First of all, they're shiny when freshly cut, they're good conductors of electricity, and they are solid at room temperature. Couple of trends to remember as we go down the group. As we go down, then the density increases and the melting point decreases. Now, hopefully this is an experiment you actually did in class, or at least had shown to you in class. So you had a big bowl, which is obviously filled with water and probably a bit of universal indicator. And then we chucked in some lithium and you saw it fizz around rather slowly and dully on the surface there. When the sodium went in, then that turned into a molten ball on the surface, moved around really quickly. And the potassium was the one that caught fire, burnt with that lilac flame, moved really quickly and may have exploded if your teacher put in a large enough chunk. Now, the good news about these is because they're all in group 1, then the word equation and balance symbol equation is pretty much identical. The only thing that changes is the metal itself. So, general word equation first of all, metal plus water makes the metal hydroxide plus hydrogen. So all you need to do there is change the word metal for the name of the metal from group 1. So lithium plus water makes lithium hydroxide plus hydrogen. Balance symbol equation, all you need to do to make sure it is balanced, hydrogen goes around as H2, remember, and then 2's go in front of your water and your metal hydroxide. Then that means it will be balanced every time. In terms of why group 1 elements all react in a similar way, then the reason for that is down to their electrons and the shells. So group 1 elements all have 1 electron in their outer shell. So what we actually find is the reactivity increases as we go down the group, because as you go further down the group, there's more and more shells, which means that 1 outer shell electron is lost more easily. So the more easily it's lost, then the more reactive that metal will actually be. So what we find is the reason it's lost more easily is because the further from the nucleus it is, the weaker the force of attraction there. This isn't for AQA GCSE, this is OCR Gateway, although some of the content might be the same. I don't teach AQA, so I can't guarantee it, however. Second group we're going to look at are group 7, the halogens. Now, these ones are always found as diatomic molecules. Now, those in my class know how much they really bugged me on one of their previous mock exams by just writing them as Cl. They forgot the little 2 in the bottom right. If you do that, your balanced equations are going to be wrong every single time. So diatomic means they go around as a pair of atoms all of the time. In terms of the colours and the states at room temperature, we start off at the top with them as gases, and as we go down, it changes to liquid with bromine, and then solids for iodine and astatine. They start off with pale colours at the top, with fluorine being pale yellow, chlorine is a green gas, bromine the orange liquid, iodine a grey solid, and then astatine dark grey or black. As long as you remember chlorine, bromine and iodine, you can work out fluorine and astatine. Some typical properties of them, they're brittle when solid and they're poor electrical conductors. And then the trends as we go down the group, they go from gas to solid, as we've said, their melting and boiling points increase, they get darker in colour, and the density increases. When we're looking at the reactions of group 7, our halogens, then they react with metals to produce salts. And if we're talking about our halogen, remember, it makes a metal halide. So do go careful when we're writing these down as a word equation to get the endings right. So when we're actually looking at something in group 7 on its own, then that is obviously chlorine, fluorine, bromine, iodine, astatine. They all end in INE. But when it's combined with the metal, it becomes the IDE ending. So chloride, fluoride, bromide, etc. As we go down the halogens, we know the reactivity decreases. Now, if we think about group 7, they all have 7 electrons in their outer shell, hence why they all carry out similar reactions. What they're going to do, therefore, is as they're moving further and further down, the number of shells increases, and they're going to try and gain 1 electron. But the pull from the nucleus is much weaker, therefore it's harder for them to gain that electron the further down the group we go, hence lower reactivity. Do remember that when they gain an electron, then they've got a full outer shell, but they also form an ion with a single negative charge. When we're looking at one of the common reactions of our halogens, then we have the halogen displacement reactions. So the halide is a compound of a halogen and one other element, which is usually a metal, but it could be hydrogen. And in our displacement reaction, then the more reactive halogen will displace a less reactive halogen from the halide. So if we've got chlorine on its own and something like sodium bromide, then what happens is the bromine is displaced by the chlorine because chlorine is more reactive. So we have sodium chloride and bromine. For those of you doing the higher tier, we need to know about the half equations that we can use to model what happens to each reactant. So if we're thinking about this same reaction, then we start off with Cl2, so our chlorine, and it's going to gain an electron on each chlorine. So what we end up with is 2E- being added, and that gives us 2Cl-. Because we're actually gaining electrons, then it's a reduction. So go back to using oil rig. Oxidation is loss of electrons, reduction is gain of electrons. In terms of the oxidation, we'll have our 2 Br- ions, and they will form Br2 plus 2E-. The next group is the noble gases. So this is for foundation and higher folks. So the noble gases are on the far right-hand side of the periodic table in group 0. So what we actually find is they're called the noble gases because they're actually very unreactive. So that means they're not taking part in many chemical reactions at all. What we find is they are non-metals, and hopefully from the name we all worked out that they are gases at room temperature. The reason they're unreactive is because they all have a full outer shell of electrons. Because of this, they go around as monatomic, which means a single atom with weak forces of attraction between them. And that's why they've got those low boiling points, because those forces of attraction are very easily overcome. Now, as we go down group 0, a few trends we do need to remember. The attractive forces between the atoms get stronger, the boiling point increases, and the density increases. So one thing to bear in mind when you're looking at all of these trends in the different groups, one of the old favorite questions they used to have was they'd give you a graph with one of the bars missing. So what you have to do is look at the differences between the existing bars and work out what the missing bar is or the missing number from a table. So do go careful with this, don't just go very general. Actually work out the differences because they're quite picky about the range they're going to give you. When we come on to the reactivity of our elements then, hopefully we remember metals form positive ions, and the more easily that happens, the more reactive the metal is. And those metals can react with water or acids if it's more reactive than hydrogen. So if we think about the two general word equations we need to remember for this bit, metal plus water makes the metal hydroxide plus hydrogen, just like we saw with group 1. And a metal plus acid makes a salt and hydrogen. And remember, the name of the salt is going to come from, first word is the metal, and the second word is which acid we have. So if we've got hydrochloric acid, it's a chloride, sulfuric acid, a sulfate, phosphoric acid is a phosphate, and nitric acid, a nitrate. So just make sure you know those endings, because they could very well ask you to name the salt, because that is one of those assessed practicals. If we've got a reaction where we're making a gas, then the volume of gas we produce in a certain time can be used for us to work out the rate of this reaction. So the faster the rate, the more gas we make. Now, we've got a few different ways that we can collect the gas, which again comes under those assessed practicals they could ask us about. Simple one is we can count bubbles. Downside to that is the bubbles are all different sizes, therefore different volumes of gas. Very easy to miscount them as well. Simple upgrade is have a measuring cylinder filled with water, which is then upturned in a water bath with the delivery tube going inside. As the gas is produced, pushes the water out, and then you can read the volume off there. Obviously, some possible errors there could be that the delivery tube comes out from under. You could have a little air bubble in the top of your measuring cylinder where you flipped it and put it under the water. So the most accurate bit of equipment we can use for measuring the gas is a gas syringe. When we're considering displacement reactions then, we also see these with metals. So the more reactive metal will displace the less reactive metal from solutions of its compounds. Now, we do have, obviously, a long list of the reactivity series. Are they likely to ask you to remember everything on it? Probably not. If you remember where hydrogen is and which ones come below, so copper, silver, gold, and platinum, there's only the 4. So if they come beneath hydrogen, remember, it's not going to react. So we can simply say they're not going to react to that point. With our displacement reactions, again, we need to do the half equations there, so oxidation and reduction. So if we're considering the reaction of copper and silver nitrate, for example, which will make copper nitrate and silver, because it's a displacement that we're seeing there, then our half equations will focus on copper for our oxidation and silver for our reduction. Now, if you want to look at those in more detail, I'd suggest you head on over to the C4 playlist and look at that part of the reactivity of elements video, because trying to explain it without actually having the visuals is a little bit tricky for you to visualize. Do remember, though, that if we have both an oxidation and a reduction happening, we refer to it as a redox reaction. So if they say, what is a redox reaction? Quite simply, it's where we've got a reduction and oxidation reaction occurring. Few useful patterns just to remind you about. Group 0, don't react. Group 1 and 2, more reactive as you go down the group. Group 7 becomes less reactive the further down the group you go. Groups 1 and 2 are more reactive than the transition metals, and metals may form ionic compounds with the reactive non-metals. Hopefully you remember that from our earlier chemistry work, which I wouldn't discount them putting a question in there based on the biology paper on Monday. And reactive non-metals may form covalent compounds with each other. So metal and non-metal, ionic, non-metal and non-metal, covalent. One of the things we do need to be able to do is to describe the different tests that we can carry out to identify what random gas we've made in any given experiment. So first one, carbon dioxide. This is where we've got lime water that goes from colourless to cloudy. So if you've got lime water going from colourless to cloudy, carbon dioxide is present. Now, lime water itself is calcium hydroxide solution. And what happens is the calcium hydroxide reacts with carbon dioxide to produce water and calcium carbonate. And the calcium carbonate is the white precipitate that you see, hence why it goes cloudy or milky. In terms of our second gas, we have chlorine. Now, chlorine dissolves in water to form an acidic substance. So what we find is it's actually going to bleach substances. So the test for chlorine is we have a bit of damp blue litmus paper, and when you hold it near the container with the gas, if it goes red and then white, then it's chlorine. So it goes red because it's acidic first of all, and then it bleaches it so it goes white. Third gas, hydrogen, that's where we have a do remember, if they ask you about a safety precaution in any of these, then you don't ever inhale gases directly from a container. So you wouldn't get a test tube filled with chemicals, stick it straight under your nose and inhale deeply. What you'd actually do is hold it relatively near and then do the royal wave to waft it gently towards your nose and take a cautious sniff. Don't inhale deeply because a lot of chemical gases we make aren't actually that pleasant. So for those of you doing the combined science, then that is all you need to know for C4, which is nice. For those of you doing GCSE chemistry, we're going to go back to just the triple stuff a little bit later on once we've done all of the combined and triple bits. So C5 then next is looking at the concentration of solutions for those of you doing the higher tier. Now, one of the key things here that they could be a little bit sneaky on is they could give you things in centimeters cubed or decimeters cubed that you need to actually convert. So if we're converting centimeters to decimeters cubed, we divide by 1,000. If we want to convert decimeters cubed to centimeters cubed, we multiply by 1,000. Now, if we're looking at how we're going to calculate the concentration in grams per decimeter cubed, then it's the mass of the solute in grams divided by the volume of the solution in decimeters cubed. If you're looking at the concentration in mole per dm cubed, the amount of solute in moles divided by the volume of the solution in decimeters cubed. So basically it's amount, whether it be grams or moles, divided by volume, and that gives you your concentration in each case. Now, one of the big things, they used to actually love this on the previous one, and I used to tell my groups that if it doesn't come up as a 6 marker, then I'd be amazed, is rates of reaction. I'm not going to guarantee it's going to be a 6 marker tomorrow because we know we've only got one that's popping up, but it's a good chance. So when we're talking about the rate of reaction, it's basically looking at how quickly reactants are used or products are formed. And we just do the amount divided by time to work it out. So as we said, if it's using gases, we've discussed the techniques we can use. Counting bubbles, upturn measuring cylinder, gas syringe. Make sure you do read any methods they give you carefully to identify what things the students in their questions actually forgotten to do. Have they measured volumes? Have they measured masses? Is it at one temperature? That's obviously ways that you can improve the experiment. So just look out for those subtle things that are missing from the method they give you. In terms of calculating rate, they could, as they gave us on the biology paper on Monday, ask you to plot a graph. Now, that's actually quite nice because graph questions tend to be 4 to 5 marks, which is a nice big chunk for basically drawing some axes, labeling them, sticking points on with a line of best fit. Fingers crossed they're going to give us a nice one on the exam tomorrow as well. So they could give you a table of results for a rates of reaction experiment, plot the graph on the bit of graph paper they give you. Remember to use a pencil because if you make a mistake, you've got one piece of graph paper and that's it. So pencil means you can rub it out. You do it in pen, you've just thrown away those marks because drawing a little sketch to the side is not going to cut it, I'm afraid, folks. It's not accurate enough. Your points have to be within half a square. That's what they're looking at. So go very careful on plotting it. Don't rush it. Now, if we're actually asked to calculate the mean rate of reaction, then what you'd actually do is have a look at your 2 points, work out the difference in volume and the difference in time and divide it. So that'd be a question where they're saying calculate the rate between 60 and 100 seconds. So 60 to 100 is 40 seconds, whatever the change in volume there is from your graph, and then you can just divide. So that's a nice, easy one. The one that they could be particularly mean about is if they ask you to calculate the rate at one specific point. So if they would say, what is the rate of reaction at 80 seconds? Then you don't just go look at 80 seconds, how much gas, and divide. Don't do that. This is where we need to draw a tangent to the curve, which hopefully you've done in maths. I know you all think you've finished maths today. Still got 2 science papers, which means there's maths coming, folks. So to do your tangent, you put a ruler against the point on the curve you're investigating. Just adjust it so that you've got equal distance from the curve on each side of the point. Draw your line using the ruler and then just plot your right angle triangle. Gives you the difference in time, the difference in your volume, and then just divide again. Obviously, when we're looking at rates of reaction, they could give you a number of different experiments. I'm not going to try and go through them all because, as I say, there's a lot of different chemicals we can throw together. Now, what you need to do, though, is read the methods, as I've said, very carefully and look for those potential sources of error. times, temperatures, volumes, concentrations. Look for those key categories first of all. Whatever they're not controlling is something that's a source of error. So rate of reaction, first factor is temperature. So hopefully we remember when we increase the temperature, we increase the rate of reaction. Now, the reason for that is that as we increase the temperature, the particles are gaining kinetic energy, they're moving faster, and the phrase we're going to get really sick of in the exam is there are more frequent successful collisions. If in doubt about rates of reaction and an explanation for it, just go with more frequent successful collisions and you're on to a good start. In terms of our rate of reaction, what we find is that it's inversely proportional to the reaction time. So basically 1 divided by time is directly proportional to the rate. Second factor, concentration. So the concentration is a measure of how much solute is dissolved in the solvent. So it's kind of like when you make orange squash. If you're only adding a very little bit of water to your squash concentrate, then it's really, really strong. Whereas if you add loads of water to it, then it's quite weak. Same idea with chemicals. If we're adding a load of water to only a very small amount of our solute, then it's a low concentration. Now, what we actually find here is that as we increase the concentration, the rate of reaction also increases. So what we find is in higher concentrations, the particles are more crowded, so they have more frequent collisions. What we do find, though, is that the reaction will come to an end when the limiting reactant has been used up. So the limiting reactant is the one that's going to run out first in our reaction. If they ask you to identify the point the reaction stops from a graph, where you get your curve, it's the point it levels off onto that plateau, that first point there, because that's where we're no longer producing any more gas, for example. Do remember that the amount of product that we produce is proportional to the amount of our limiting reactant. Third factor is pressure. So if we increase the pressure, then the particles become more crowded, so we get more frequent collisions again, and therefore the rate increases. You're probably sensing a bit of a trend here with more frequent collisions. It's just something that you know, hopefully, just to repeat endlessly where it comes to rates of reaction. Next factor is surface area. So this is something some people find a little bit tricky to get your heads around. If you have one big lump of something, then what happens is it's actually got quite a small surface area. Whereas if you then break it up, there's more particles exposed. So what we actually have, luckily I have some random little blocks here. If you've got one lump of a particle, so if it's all just like this, all we've got are the actual exposed edges on the outside that are actually able to react. Whereas if we break it up into all of the individual little parts, we're exposing all of the inner particles as well. So what we find is if we change it from one solid lump into a powder, then we've increased the surface area. Now that means that at any given time there's more particles exposed, so that means we get a much faster rate of reaction. So what we're finding here is as the size of the lump decreases, the surface area to volume ratio increases. Now, because we've got more exposed particles, we've got more frequent collisions, hence the reaction rate increases. The only other way that we can affect the rate of reaction is by using a catalyst. So a catalyst is a substance that increases the rate of a reaction, but is unchanged at the end. So they could ask you to identify a catalyst from a table where they will have things with the different reaction rates, and they will also have the color or something like this of the catalyst. So the one you're looking for is the one that's the same color at the beginning and the end, but has a faster rate of reaction. One thing about our catalysts, they are specific to a reaction. So one catalyst won't catalyze every reaction. You have to have different ones for the different reactions. What we actually find with the reasoning behind our catalysts is that when we add it, the rate of reaction increases because it's providing an alternative reaction pathway. And the key thing about that alternative pathway is it's got a lower activation energy. So what we find there is we get a greater proportion of the particles that collide that actually reach their activation energy. Next little bit of our C5 topic is reversible reactions. Now, the key thing to remember here, first of all, is the reversible reaction arrow. So they have asked this in the past for you to draw the arrow, or what does this arrow mean? So it's just half one way, half the other way. So what we need to know is where we see that, it means it's a reversible reaction. So that means it goes forwards and backwards. In terms of some of these reactions you might have seen, then things like hydrated copper sulfate, that's probably the example you've seen there, where it goes from blue to white and vice versa. One thing we do need to know is when we're talking about a closed system, this is one that's like a flask with a stopper in it. So in this, nothing can enter or leave. So if we've got a reversible reaction taking place in a closed system, it will reach equilibrium. Now that means that the rate of our forward reaction and the rate of the backward reaction are equal to one another. So what we find is the concentrations of all reacting substances will remain constant. Do remember we call it a dynamic equilibrium though, because the forward and backward reactions are still happening. So it doesn't just get to this point and then everything grinds to a halt. You still have the forward reaction and backward reaction happening. So dynamic, it's constantly happening, but the actual concentrations of the products remains the same. For those of you doing the higher tier, we need to know about equilibrium position. So when we're talking about equilibrium position, it's a description of the relative amounts of reactants and products in a reaction mixture at equilibrium. So the equilibrium position is on the left when the concentration of reactants is greater than the concentration of products. And the equilibrium position is on the right when the concentration of reactants is less than the concentration of products. However, it's not a fixed position. It can change with changing conditions. So this is just the higher tier, remember. First one is the pressure. So if we increase the pressure in our reversible reaction, then the equilibrium position will move in the direction of the fewest moles of gas. So you look at the balance symbol equation, you count the moles of gas, and remember gas is given by the G in brackets after the chemical, and then whichever one has the fewest moles of gas, that's the direction that the actual equilibrium position will move to. So if we have 3 moles of gas on the left and 2 moles of gas on the right, if we increase the pressure, equilibrium position moves to the right. If we think about concentration as our second factor, if we increase the concentration of a substance, then the equilibrium position moves in the direction away from the substance that we've got the increased concentration of. Third one, temperature. If we increase the temperature, then the equilibrium position moves in the direction of the endothermic change. So hopefully we know the endothermic is a plus sign in front of the delta H. So if it's a minus sign, it's exothermic. So you need to look to see when they give you the actual equation, look to the little bit on the right where it has delta H. If it's a minus, that means the forward reaction is exothermic. So if we were to increase the temperature, then it would move the equilibrium position to the left, and vice versa if they gave you a positive sign. Now, hopefully that's cleared up the equilibrium position bits, because I know that's a little bit tricky, but as long as you remember those 3 key things, so pressure towards the fewest moles of gas, concentration away from the substance with increased concentration, and temperature in the direction of the endothermic reaction, then you should be able to actually get the marks on that bit. Now, the next thing we're going to have a little look at is C6. So this is where we all come back, so foundation and higher folks. First thing that we had a look at was extracting metals. So we have the word ore, which just refers to the rock or mineral that contains enough metal to make it economical to extract. And there are 3 that they're going to potentially ask you the names of. So malachite is copper carbonate, bauxite is the aluminium oxide, and hematite is iron oxide. So malachite, copper, bauxite, aluminium, hematite, iron. Make sure you know those just in case they throw in an easy 1 marker there. Now, what we actually do is, in order to get these ores, first of all, we have to extract them by carrying out mining, and then we've got to process them to separate the metal from the other chemicals it's joined to. Now, the method that we're going to use to actually extract the metal depends on its position in the reactivity series once more. So, two key methods we can use. First one, electrolysis. Big downside, it's expensive. Positive, we can use it to extract all metals. Second method is heating it with carbon or carbon monoxide. Advantage, it's cheaper. Downside, it only works with metals that are less reactive than carbon. So if we think about copper as our first metal, what we actually have is the extraction of copper from copper-2 sulfide is going to happen in two stages. So the first one is that we roast the copper-2 sulfide in air, so that we have copper-2 sulfide plus oxygen, which makes copper oxide and sulfur dioxide. And then we heat our copper oxide with carbon. So as a result of that, we make copper and carbon dioxide. So this is again an example of a redox reaction, and the carbon is the reducing agent. Another way that we can actually reduce our copper-2 oxide to copper is by heating it with methane or with hydrogen. So just bear that one in mind as an alternative technique, just in case they get a bit mean and ask that one. The next one that they've reintroduced after many years is how we extract iron. Now, this is done using a blast furnace. So three raw materials we need to remember: iron ore, which is hematite, coke, and limestone. So what we actually have here then is a multiple stage reaction. That's our blast furnace, which hopefully we remember. So the first thing is that the coke is going to burn in hot air to make carbon dioxide. So carbon, just C, plus O2 makes CO2. Stage two is the coke reduces the carbon dioxide to make carbon monoxide. So C plus CO2 makes 2CO. Stage three, our carbon monoxide reduces iron oxide to iron, and this takes place at pretty high temperatures, about 1,500 degrees Celsius. So 3CO plus Fe2O3 makes 3CO2 plus 2Fe. Are they likely to expect you to memorize those equations? Probably not. Could they ask you to do the balanced equation and not tell you what carbon monoxide, carbon dioxide are? Yes. So be mindful of that you may be asked the balance part of this equation, if nothing else. What we actually find then is, as a result of the iron that we've got, it's not pure. There are impurities still in there, and we need to actually remove those impurities to avoid the properties of the metal being altered. So what we do is, one of those raw materials was limestone, if you remember, and we use the limestone to remove those impurities. So first stage is calcium carbonate will decompose in the high temperatures. So CaCO3 forms CaO plus CO2. So it's a thermal decomposition reaction. And then the second stage, calcium oxide reacts with silica to form calcium silicate. Now, what we find then is that this is forming a stuff which everyone finds amusingly called slag. And the slag is less dense than the iron. So the iron runs off at the bottom and the slag runs off at the top. So that means that we've then got pure iron, any impurities removed from the slag, job's done. Next one that we're going to look at is extracting aluminium. Now, aluminium is usually found as aluminium oxide, and we've got to extract it by using electrolysis. And the reason for that is that aluminium is more reactive than carbon. So we can't heat it with carbon because nothing would happen. Big thing to remember here is that our aluminium oxide has a really high melting point on its own. So in order to heat it to the temperatures to melt it wouldn't be great in terms of the cost. So what we do is we actually dissolve the aluminium oxide in a substance called cryolite, and that's going to allow electrolysis to happen at roughly half the temperature it did before, at 950 degrees Celsius. What we find in terms of our electrolysis cell then is we've got it lined with the actual graphite. So you can see around here, we've got a graphite lining all the way around there. Now the graphite lining actually acts as the cathode, and then these blocks up here, which are also our carbon anodes, those ones are the anodes, as I just said. Now, what we find when we pass the electricity through this, then oxygen is produced at the anode, and it will react with the graphite, which is just carbon, and it makes carbon dioxide. At the cathode, we will have our aluminium produced. Hopefully we do remember why, because if our cathode is negative, it will attract positive ions, the aluminium, whereas our anode is positive, so it attracts negative ions. For those of you doing the higher tier, you do need to know the half equations for this. So at the cathode, Al3 plus 3E minus makes aluminium, just Al. And then at the anode, 2O2 minus makes O2 plus 4E minus. What we do now need to go on to for the higher tier folks is the biological metal extraction, which one of you asked about a moment ago. Now, the first problem that we find is where we've carried out all of this mining in all these different countries, we don't keep using the same mines years and years and years on end. So they become abandoned. Now, the big downside to that is abandoned mines will often flood. Now, that's going to lead to the oxidation of metal sulfides to sulfuric acid, and the acid will then react with the metal ores, creating soluble metal compounds. Those soluble metal compounds are then carried in water as it drains from the mine. So what we find in bioleaching is that bacteria will oxidize iron and sulfide ions. So sulfuric acid will form when oxygen and water are present, and the sulfuric acid will break down copper sulfide ores to release the copper ions. So a few advantages of this, first of all, it works on these low-grade ores, so we don't need very high quantities of the metal ore in the ground to actually get metal from it. It's cheaper than traditional mining, and obviously that is always a bonus when we're talking about any industrial technique. The bacteria occur naturally and need no special treatments, and it doesn't release sulfur dioxide into the atmosphere, unlike some of the other extraction techniques. Two key disadvantages to remember: it's slow, and we may produce toxic substances. Still, for the higher tier, we also need to know about our phyto-extraction. So some plants that we have available in the world are actually very good at absorbing certain metal ions, and those metal ions then accumulate in their roots, shoots and leaves. So basically the plant takes in these metal ions and it builds up inside the plant itself. So what we actually do here is we use those plants and we grow a crop of them on soil that contains low-grade ore or mine waste. We'll also add a chemical called a complexing agent, because it's then going to make it easier for the plants to absorb the metal ions. Once they've actually done that, we harvest the plants, we burn them, and we get this ash with a high concentration of the metal ions. We can then extract the metal from the ash, and then we use it like it was a high-grade ore. So it's a way that we can actually extract metal from these areas where it's only very low quantities of the metal ions present, without any real stress from us at all. We're just growing plants on a field and burning them a bit later on. So 4 key advantages. First one is cheaper than traditional mining and processing. Secondly, there's less waste. Third, there's smaller energy transfers involved, and it's close to carbon neutral. So carbon neutral just means that as the plants are growing, they take carbon dioxide from the air into themselves during photosynthesis, and then when we burn them, they release the same amount of carbon dioxide, because we can't just generate extra carbon from nowhere. Some disadvantages though: it's slow, and the crops may need replanting and harvesting for years before we've actually removed all of the metal from the soil. Foundation and higher folks now, we need to know about how to choose materials. Now, what they're going to do in all likelihood, if this comes up, is they will give you a table with a variety of properties of 3 or 4 different materials. And then they're going to ask you to select which material is best and explain or justify your answer. So for those, all you need to do is have a look and see what's the actual use of the object first of all, and then look at the relevant properties. There will be a column on there that makes absolutely no difference. So they had one a few years ago about the material used to make an aircraft wing, and one of them was their ability to conduct electricity. No one cares. it's a wing of an aircraft. It doesn't matter whether it conducts electricity or not. It's irrelevant. What it needs to be, however, is lightweight. It obviously needs to be malleable and strong. Any of those would have been good answers, which you'll get from the table. So when they give that to you, do think which properties are relevant and include the actual numbers. If you are saying that something has a low density, then don't just say it's light. Won't get the marks for that. You need to say it's lightweight. Picky, I know, but it is one way that people throw away marks. One of the things we do need to consider when it comes to choosing materials is something called a life cycle assessment. So these are cradle to grave analyses of the impact of making, using, and disposing of a manufactured product. So any industry that's actually generating a product will carry out these life cycle assessments. So in there, they'll be looking at data about sustainability, the environmental impact, its lifespan, if we can recycle any of the product, and how easy it is to actually dispose of all of the different materials. What they're going to do once they've carried out this assessment is look at it and think, are there stages in there that could be improved, or could we find an alternative material that does that same job that's potentially less harmful? So just have a little look at what they give you on that and think, is there something here that looks like it's actually quite wasteful, that something's not sustainable? Does it say this can't be recycled, or it produces toxic byproducts? Those are the things we want to swap out. One of the things that we do need to think about when we come to that end of the life cycle of our product is what happens to it. So quite often, any rubbish that's not recycled, which is still quite a large proportion, will end up in landfills. Now, we should all be recycling now. The councils have generally made it easier by giving you different ways to just put recycling out with your normal waste, etc. And recycling is actually a very important thing for us to do. Firstly, it's conserving raw materials and energy resources. Secondly, we're reducing the release of harmful substances into the environment by putting them into landfills. And finally, we're reducing the waste, which is always a good thing to do. In terms of when we're considering this whole process of recycling, we need to consider a few things here. First of all, how easy is it to collect and sort the waste? So what you'll find is that some of you might have just one giant bin that you throw all of your recycling stuff in, and then it's taken somewhere and sorted by the council. Others of you might have about 4 different things that you've got to put paper in one, glass in another, metal in another one, and so on. So thinking about that is important, because the easier something is for people to do, the more likely they are to do it at the end of the day. Now, what we also need to do is think about the amount and type of byproducts that we release when we carry out recycling. We need to think about the amount of energy involved at each stage and the cost of recycling compared to disposal in landfill or incineration, which is burning the waste. Now, hopefully we did sort of recall a little video or something like this about how the actual process goes on for recycling. So once the materials are collected and sorted, metals get melted down and poured into molds to produce these things called ingots. If we're talking about paper, we mix it with water, clean it, roll it, and heat it to make new paper. If it's glass, we melt it and mold it into our new objects, and polymers are melted and formed into new objects. So generally speaking, if in doubt, go with heat it in some way and mold it into a new shape. The next bit we come on to for everyone is using alkanes from crude oil. Now, crude oil is massively important to us in our modern society, but it is a fossil fuel. So that means that it was formed from the remains of living things that lived in the sea millions of years ago. So they died, became buried on the seabed, and eventually turned into crude oil over millions of years. The downside here is it's a non-renewable resource. So this means that once we've actually used it up, then it's not forming again anytime soon. And we're using it up at a faster rate than it's being reformed. One phrase to avoid at this point, if they ask you what non-renewable means, don't say that we can't use it again, because that's wrong. Okay, it's the fact that we're using it at a faster rate than it's being formed. 2 other fossil fuels we've got, natural gas and coal. Do remember they could also throw in the word finite here. So finite just means something's going to run out. There's a limited amount of it. Now, because they're actually being used up fast, they're being made, they're all a finite resource. They are going to run out at some point. When we're thinking about the crude oil that we get out of the ground, then it's a mixture of different hydrocarbons of all different lengths. Now, that's not useful to us. In order to make it useful, we need to separate them into each individual fraction. And we do that in the process of fractional distillation. So this is a link back to the work we did in C2 about separating techniques. Hopefully we remember that hydrocarbons have different boiling points depending on the length of the chain. And we've got our fractionating column here. So the fractionating column then is just going to have a temperature gradient. So it starts off hottest at the bottom, and then the further up you go, the cooler it gets. So what happens is we put the oil in at the bottom here, and then it's going to evaporate the smaller fractions, which can move further and further up the column. The smallest ones lost at the top as LPG. Next one down is petrol. Then we've got paraffin, diesel, heating oil, fuel oil, and then bitumen at the bottom, which is the one with the highest boiling point. So we're separating it all based on the boiling points. So that's the key thing to remember here, is that fractional distillation works because the different fractions have different boiling points, all determined by the length of the chain. The longer the chain, the higher the boiling point, the lower down it comes out of the column. Now, that could be one that could ask you for a slightly larger number of marks on the question, because we can talk about hydrocarbons having different boiling points, more carbon atoms, longer molecules, stronger intermolecular forces, therefore higher boiling points. Temperature gradient with the hottest bit at the bottom, coolest at the top. And then as the vapors rise, they condense and run off to be collected into those individual fractions. Plenty to say to pick up some marks there, as we can see. Now, one thing that we do need to remember here in terms of bonding is the atoms within the hydrocarbon itself are held together by hydrogen bonds. So the carbon onto the hydrogen, the little line that they draw there, that is a covalent bond. And covalent bonds are much stronger than the intermolecular forces. So when we heat crude oil, what's happening is the intermolecular forces are broken, but the covalent bonds are not broken. So the molecules aren't breaking apart. It's just that the individual molecules that are just attracted to each other at cooler temperatures are separating because the intermolecular forces are being broken. One of the big problems about our crude oil, though, is that when we've gone through this process of fractional distillation, then we've actually got a lot of fractions of some and not much of others. And one of the key things that we don't get enough by just carrying out fractional distillation are things like petrol for all of our cars. So in order to actually make sure that we can meet the actual demands, then we can carry out a process called cracking. And cracking converts large alkane molecules into smaller, more useful ones, an alkane and an alkene. So what we actually find is that we need two important things: catalyst, which will be alumina or silica, and a high temperature. So when we actually have our large alkane molecule with a catalyst and a high temperature, we'll split it into one alkane and one alkene. And that means that we can generate more of the smaller fractions like petrol to meet the actual demands. One thing to bear in mind as to why this is important to do: large alkanes aren't actually very useful to us. They don't flow easily, they're hard to ignite, so we can't put them in our cars and run them like that. So what we actually need to do is get rid of the large quantities of the large alkane molecules we've got, where we've got way more than we actually need, and generate more of the smaller ones, which are more useful to us. So the last bit, for those of you doing the combined science, is all about the atmosphere and water at the end. So first thing, we need to know how the atmosphere on Earth actually formed. Hopefully we know the Earth is about 4.54 billion years old, and in the early stages of the planet's development, it was very volcanic and generally an unpleasant place to try to live, hence nothing did. And as those volcanoes were erupting all over the shop, then they released huge volumes of water vapor and carbon dioxide. As the Earth began to cool, water vapor condensed, and the oceans formed. That meant our atmosphere was mainly carbon dioxide with some small amounts of ammonia and methane. Bit later on, plants evolved. You don't need to know the full mechanisms of it. That's going a little bit higher than just GCSE. So once we've got algae in plants that have occurred, then photosynthesis takes place. And as a result of that, carbon dioxide levels in the atmosphere decreased and oxygen levels increased. Hopefully we remember that photosynthesis is carbon dioxide plus water, makes glucose and oxygen. Once we actually had this taking place, the oxygen made in the oceans was reacting with metals to make metal oxides. Now, after most of the metal that was floating around had been oxidized, any free oxygen that was left began to accumulate into the atmosphere. And eventually we got to the point that we have today. And you do need to know these percentages. They used to love it as a one marker to label part of a pie chart. So what we actually have, nitrogen 78%, oxygen 21%, carbon dioxide 0.04%. So those are the only ones they're going to ask you to remember. Most likely to are nitrogen and oxygen, but I can't guarantee they wouldn't ask you about carbon dioxide. So make sure you know the composition of today's atmosphere. Next thing we need to know about is what we're doing to our atmosphere. And the key problem is pollution. So pollutants are substances released into the environment that may harm living things. And one of the key ones we've got is carbon monoxide. So when we've got incomplete combustion of fuels, then we produce carbon monoxide. And what we find is this is very commonplace in vehicle engines because there's a pretty poor supply of oxygen there. So the hydrocarbon plus a limited amount of oxygen makes carbon monoxide plus carbon plus water. That's our incomplete combustion. Now, the big downside of carbon monoxide is it's colorless, odorless, and tasteless, which means it's actually very dangerous as a gas and kills large numbers of people each year. So what we actually find the reason it's going to kill people is the carbon monoxide binds to your hemoglobin inside your red blood cells, and it reduces their ability to carry oxygen. So that means you're going to be quite drowsy, you're going to have difficulty breathing, you'll feel quite sick, you'll get a headache. And if you don't actually leave that area and get lots of fresh oxygen, then it can lead to death as well. So just be mindful of that side. In terms of particulates, these are small particles produced during incomplete combustion or industrial processes. And the big downside to breathing those in is that they settle deep in the lungs when you breathe them in, which causes bronchitis. Some other breathing problems we don't need to specify, and it increases your chance of heart disease. Another big issue we've got is nitrogen. So that when we've actually got nitrogen and oxygen, then they don't normally react together, hence 78% nitrogen, 21% oxygen in our atmosphere. The reason that it doesn't usually react is because nitrogen has a triple bond between its atoms. So that requires really quite high temperatures in order to break a triple bond. But inside vehicle engines, we have the high temperatures. So the nitrogen reacts with oxygen to make nitrogen monoxide, and then that nitrogen monoxide is oxidized into air to make nitrogen dioxide. So these are problematic because when they dissolve in the water vapor of our clouds, we get acid rain that falls. And acid rain will kill trees, it can kill living things in lakes and rivers, corrode metal, generally lots of bad things there. If we're actually burning fossil fuels, then quite often we make sulfur dioxide because they contain these small amounts of sulfur compounds. Now, sulfur dioxide also causes acid rain, and it can also cause breathing difficulties when you breathe it in. In terms of the next problem, climate change, so we have three greenhouse gases: carbon dioxide, methane, and water vapor. So what we actually find happening here is when we're carrying out processes that generate larger quantities of the greenhouse gases, so burning fossil fuels generates all the carbon dioxide, for example, then what we would find is that the energy that's transferred from the sun that reaches the Earth's surface, that's going to warm up the surface of the Earth. That's all perfectly natural. And then what happens is the infrared radiation is emitted by the Earth's surface, and normally a large proportion would actually go back out past the atmosphere into space. and that means our planet would stay at about the same temperature. Downside, though, is that when we've got more of those greenhouse gas molecules present, then that will be absorbed by those greenhouse gas molecules. As a result of that, they then emit infrared radiation in all directions, leading to the warming of the Earth's surface and the atmosphere. Now, what we actually have is something called anthropogenic activities, which are just human activities, which can increase the amount of greenhouse gases in our atmosphere. And as a result of these increased greenhouse gases, we have what's called the enhanced greenhouse effect. So because we have an atmosphere that contains carbon dioxide and small amounts of methane, then what we actually have is the fact that our planet has a temperature, because they are going to trap a certain amount of the infrared radiation from the sun. Without that, no life could exist here. So what we're doing is, when we're producing more of the greenhouse gases, then we're getting an enhanced greenhouse effect. So that means we're getting an increase in the mean surface temperature of the Earth. What we do find is that in terms of the carbon dioxide, as I've said, is combustion of fossil fuels. So more cars on the road, more industry, all of those ideas are great. In terms of methane, then what we've got, things like paddy fields, more cattle, etc., then all of those things are actually going to be increasing the methane levels in our atmosphere. Downsides, if we've got climate change and the temperatures are increasing, ice caps melt, we get more flooding, we get droughts in different parts of the world, and extreme weather events. So all of those are problems of climate change. In order to reduce greenhouse emissions, then we need to reduce our consumption of fossil fuels, maybe by switching to use renewable energy sources as opposed to fossil fuel-based ones. We can also use carbon capture techniques to stop the carbon dioxide escaping when any fuels are used as well. So even if we are experiencing some of these effects, we can also protect against them. So we can build flood barriers like the ones we've got in the Thames. We can change buildings so they're actually able to withstand these extreme weather events. The very last bit for the combined science, folks, is looking at how we generate the water that we drink. So first thing, and they used to ask this for a 1 marker, was where does water actually come from? So lakes, reservoirs, aquifers, rivers, any of those, absolutely fine as answers. Possible contaminants that we will find in them, though, we could have insoluble material like soil and leaves that have just fallen in, soluble substances like salts and pollutants, and microorganisms. So all of those are possible contaminants to our water supply. We've got 4 steps to basically get us water that we can drink safely: filtration, sedimentation, another filtration, and chlorination. So our first filtration is all about removing large objects. Sedimentation is where bits sink. Next filtration removes small objects, and then chlorination to kill the bacteria. So what you've probably seen is a diagram something like this one. So we start off with our reservoir, and then the water is going to pass through these grates, which are acting as an initial filter to get rid of things like leaves and twigs and sticks and things like this. From there, we carry on to our settlement tank. And what happens is things like sand and so on will sink down to the bottom. We can then run the water further down, and what we do is we add ammonium sulfate and lime, because what that does is it actually makes the different chemicals clump together. So we've got little light bits like clay. They stick together and again sink down to the bottom. Once it comes through here, we've then got a bed of very fine sand, and again it's a filtering process. And then finally, as we come along here, we're actually going to add chlorine to it, because chlorine kills any of the bacteria that's present within the water before it comes off to our homes, where it's then nice and safe to drink. So one other option people have, rather than using freshwater sources, is using a desalination plant. Now, that's only going to work if you've got lots of seawater present, because desalination is the process that removes salts from seawater to make potable water, so drinkable water. If we're using small-scale desalination, then we use reverse osmosis, which uses ultrafilters to get rid of the salts. Large-scale desalination uses simple distillation. So for those of you just doing combined science, that's it. That's all you need to know for your exam tomorrow. So what I'd suggest you do is head on off and do individual revision. Obviously, if there are bits that we've gone through you're not sure on, then the combined science playlists on C4, C5, C6 are on my channel as well. For those of you who are doing separate science and therefore doing the GCSE chemistry paper tomorrow, we're now going to go through the separate science bits from C4, C5 and C6. So in terms of our transition metals, which we didn't mention when we we're looking at our periodic table, they're the ones in the rectangle in the middle. So you've got group 1, group 2, this weird little rectangle bit, and then the other groups on the right-hand side. So that rectangle are the transition metals. Now, what we actually find is, as the name suggests, they are all metals. It's not a trick. And they do have the typical properties of metals. So they're shiny when freshly cut, good conductors of electricity, strong, malleable, you name it. It's a metal property, and they've got it. If we compare group 1, our alkali metals, and the transition metals, then the transition metals are stronger, harder, have a higher density, and higher melting points. If they give you a compare question, make sure that you don't just say it has a high melting point or it is strong. If it's comparative, you've got to have the little ERs at the end to make it a proper comparison. In terms of the chemical properties of our transition metals, then they react very slowly if they react at all. So if we think about one common example here of good old iron, then iron plus oxygen plus water makes hydrated iron oxide, or rust as we commonly know it. If we think about metals like platinum, then that won't react with water or oxygen. So two different transition metals, one reacts incredibly slowly, the other doesn't react full stop. One thing to remember about our transition metals is that they can form more than one type of ion. So the way you know what the charge on the ion is for a transition metal is look at the Roman numerals in brackets. So where it's got iron oxide, between those two words, there's going to be Roman numerals in brackets. Hopefully you know the basics of basically 1, 2, 3. If they're being really mean, 4, okay? But beyond that, you don't have to know the entirety of the numbers in Roman numerals. So just 1, 2, 3, dead easy. It's I, or I. And then, of course, IV is 4. That just tells you the charge, and it will always be positive because we're talking metals. When we think about the actual compounds that are made with our transition metals, they produce coloured ionic compounds, whereas alkali metals will produce white or colourless compounds. So it's one way we can start to identify what we've got in front of us if we've got an unknown chemical compound. If it's coloured, chances are it's a transition metal. If it's white or colourless, it's probably an alkali metal. The transition metals are good catalysts, so they speed up chemical reactions without being used up themselves, and we'll use them in things like catalytic converters in cars. So they use metals like platinum, rhodium, palladium, because they convert those harmful exhaust gases into less harmful ones, so that when they're released from the car, it's less damaging to the environment. The first set of colours then, because one of the things about C4 on the chemistry is you have to know a whole bunch of colourful things. So the first test is flame colours. So what we actually find here is when you're doing a flame test, what we're actually doing is vaporising metal ions. And at that point, they're absorbing energy and electrons jump to higher electron shells. Now, when those electrons then drop back to their normal electron shell, then they transfer light energy to the surroundings and give you that colour. So it's the colour that we see that allows us to identify it. In terms of the actual practical that you would do, they could ask you how you could identify it. So to carry out a flame test, you've got a nichrome wire loop, dip it in some concentrated hydrochloric acid, and then hold it in a roaring Bunsen flame. Now, you're going to do that over and over again until the flame doesn't change colour. At that point, you know you've removed all of the contaminants and you're free to do your test. If it's a solution, you just dip it into the solution, hold it in the Bunsen flame, note the colour. If it's a powder, then you need to dip it in water, then in the powder to make it stick, and then hold it in the Bunsen flame and note the colour. 5 colours we need to know: Lithium is red, sodium yellow, potassium is lilac, calcium is orangey red, and copper is a greeny blue colour. If they ask about possible sources of error, the key one is contamination. So not cleaning the loop properly, maybe having a different bit of a chemical in whatever containers you've got them in, etc. Next test that we can use is the hydroxide precipitate test. So group 1 hydroxides are soluble in water, and most other metal hydroxides are insoluble in water. So group 1 soluble, most others insoluble. So we use sodium hydroxide in experiments for this reason. When we add sodium hydroxide to a solution that contains metal ions, we will make a precipitate. And the colour of the precipitate tells us which metal ion we actually have. Again, we've got to learn some colours here, and there's no easy way to do this, I'm afraid, folks. Iron 2 is green, iron 3 orange-brown, copper is blue, calcium white, and zinc is white. Now, what we've actually got here are two that are the same colour, but zinc hydroxide will dissolve and form a colourless solution if we add an excess of sodium hydroxide. Calcium hydroxide, however, won't dissolve. So if you end up with a white precipitate and you need to identify, is this zinc or is this calcium, you just add more of your sodium hydroxide. If it dissolves, it's zinc. If it doesn't, it's calcium. When we're talking about our next test, this is actually looking for anions. So anions are negative ions, cations, positive ions. So to test for our first anion, which is sulfate ion, then we add a few drops of dilute hydrochloric acid, and then we add a few drops of barium chloride. If we get a white precipitate, sulfate ions are present. No white precipitate, no sulfate ions. Second one is testing for carbonates. So we add a few drops of hydrochloric acid to our tube. If we get little bubbles forming, then we've got carbonate ions present, and the bubbles will be carbon dioxide, as carbonate suggests. If we want to test for halides, which as the name suggests are the ones from group 7, then we add a few drops of dilute nitric acid to remove other ions present that could give us a confusing precipitate colour. And then we add a few drops of silver nitrate solution. The colour of the precipitate tells us which halide we've got. So white is chloride ions, cream is bromide, yellow is iodide. So basically it's just the 3 shades of white that we're looking at. Is it white, is it cream, or is it pale yellow? White at the top, and then you work your way down is a nice easy way. One thing that they could ask you to do with those is they will give you a table of results that some student has apparently carried out all these experiments, and then they'd ask you what's present. So you need to have a look and see what the results of each are, and then work out which chemical is actually present. So you'd have flame test results and also things like the sulfate and carbonate test results. So when you've identified which of those are actually there, put the name together and you've got the actual chemical that was present in the first place. The next thing they could ask you about are the instrumental methods of analysis. Now, these rely on machines to carry out analysis on a substance, and they've got a few key advantages here. Firstly, they've got a high degree of accuracy. Secondly, they're very fast and can run 24 hours a day, 7 days a week. And finally, they're very sensitive, so they can analyze really small amounts of samples, which is very useful if they're expensive or if they're very difficult to obtain. First one of these is gas chromatography, which again, we looked at back in C2 as a separating technique. So go back over that just in case. Hopefully you remember that we put our sample in, we use a carrier gas, which is a non-reactive gas as our mobile phase, and it pushes it through a column that's filled with particles of our stationary phase. The detector on the other end just picks up as the samples come out the other side, and we end up with little peaks in a chromatogram at the end. So the different peaks there tell us how many different chemicals we've got and how much of each chemical we have. If we're then coming on to look and see what we can do using another technique, we've got mass spectrometers. Now, as their name suggests, they measure the masses of atoms and molecules. So what they're going to do is analyze the relative amounts of isotopes and work out the structure of a molecule. And on one of the practice papers, they actually used one of these in order to get you to work out an actual structure and draw the displayed formula for it. So what happens here is when the sample enters the mass spec, then it's ionized to form molecular ions. So as the molecular ions gain energy, they can fragment, so they can break up. As those ions then pass through the machine, the detector records the amount of each fragment. And what we then get is a mass spectrum like this. So we've got the different little bars there representing the different fragments, and it tells us the amount based on the height of the bar. Now, the key thing to remember with this one is that the one on the far right-hand side is your molecular ion peak. Now, that just tells you wherever that falls, and in this case, you can see it all the way over here at 46, then that is the actual mass of your chemical, so the relative formula mass. So you know that whatever you're drawing as a structure has to have a relative formula mass of 46. The other ones there, the different peaks, will just tell you which fragments are present, and obviously the relative height of it tells you the relative amount of it. I'm hoping they're not going to be too mean with that, but I think that you need to be prepared for them to give you a mass spectra and then ask you what the actual formula of some chemical is. So on the past one, they did give you a bit of a structure, and then you had to fill in the blanks. So if they give you the backbone of carbons, then you obviously know carbon has a mass of 12, so you can count up those and add them together, and then you can work out what the remainder is by using your mass spectra molecular ion peak. Other than that, look at the other bits of information in the question. For those of you asking about the combined, that was in the first section. The stuff we're going through now is only for those doing GCSE chemistry. So go back to the beginning of the live stream and you can see all of the bits about the combined science. Next up, C5 for GCSE chemistry. We need to know a couple of calculations here. First one is percentage yield. So your percentage yield is the actual yield divided by theoretical times by 100 to give it as a percentage. So the way that we actually do this, first of all, you calculate the relative formula masses. Then we calculate the sum of the relative formula masses using our balanced equation. So just relative formula mass times number of moles. Calculate your theoretical yield by doing the mass of your limiting reactant divided by the sum of the relative formula mass for the reactant times the sum of the relative formula masses for the products. And then you can calculate the percentage yield doing actual divided by theoretical times 100. If they're being mean, they won't give you that equation in the actual question. If they're being nice, they will. Obviously, I can't say which one it's going to be, so learn it just in case. When you've actually calculated this, you will have a number between 0 and 100. If it's not, if it's something like 368, you've gone wrong. And generally what I tell mine, flip it the other way up, because that's probably where you've gone wrong. The reasons that it's going to be less than 100% as your actual yield here is that the reactants may react in a different way than we expected. The reaction may not be going to completion, or we may lose some of the product somehow, like when we're transferring it between vessels, etc. Second calculation we need to know is atom economy. So atom economy measures how many atoms in our reactants end up in the desired product. So if we've got a low atom economy, then only a few of the atoms from our reactant end up in our desired product. Whereas if it's a high atom economy, then that means a lot of the atoms from our reactant end up in our desired product. So to calculate this, it's the sum of your relative formula masses of the desired product divided by the sum of the relative formula masses of all products times by 100. So what we find here is the higher the atomic economy of a process, the more sustainable and greener it is. If you're on higher tier, then you also need to know how we select a reaction pathway. So when we're actually considering which reaction pathway to choose, there's a few things we need to contemplate. First of all, the yield of the product. Secondly, it's atom economy, and obviously we want those to be as high as possible in both cases. The rate of the reaction, we want it to be as quick as we can. Any byproducts formed, if they're useful, brilliant. If they're toxic, we don't want those. And if it's a reversible reaction, then equilibrium position is important. So do remember that even though some byproducts may be formed in a reaction, if we can sell them for another thing, we can make it and make more profit. If, however, it's a toxic byproduct, we don't want to make those ones. So the next bit for the higher tier chemistry folks is titration, which is something that I know my students absolutely hate for some reason. Now, titration is just the method that we use to determine the concentration of an acid or alkali by using a neutralization reaction. And we use what's called a single indicator like phenolphthalein because it gives us a really clear endpoint. We don't use universal indicator because it's a nightmare to try to guess what pH that is, as you know from many experiments you've done in school. So the method for titration, because it could be one of our assessed practicals again, is you've got a burette, which is one of those big glass tubes with a little tap at the bottom, and we fill that with acid. We then use a volumetric pipette to transfer a known volume, usually 25 centimeters cubed, of our alkali to a conical flask. You add a few drops of your single indicator to it, record the start volume on the burette, add your acid until it just changes color, and record the end volume as well. So that tells you the actual amount of acid needed to neutralize. Now, what we need to do with this is you don't just do it once and take that as your actual volume. You need to repeat it until you obtain what are called concordant titers. So that means they are within 0.1 centimeters cubed of each other. And a titer is just a measured volume of solution that we add from a burette during titration. Now, in terms of the indicators, there are three that we generally use here. So we've got litmus, which is red in acidic and blue in alkaline. Phenolphthalein is colorless in acidic, pink in alkaline. Methyl orange, red in acidic, yellow in alkaline. And as we've said, the reason we use these as opposed to universal indicator is that there is a really distinct color change at the end point. So you can see exactly when it's been neutralized without any sort of doubt in your mind. Now, what we will actually come on to do then is consider some of these potential accuracy or error parts of titration. So what we actually have first of all is when you're given this question on titration, read the method that they said the student followed. One of the things they could do to give you an opportunity to talk about potential sources of error is they could get the student to measure using a measuring cylinder. Now, measuring cylinders are less accurate than a volumetric pipette. So possible source of error is inaccurate measuring cylinders, and improvement, use a volumetric pipette. With our burette, we need to make sure it's clamped vertically, because if it's on a slight tilt, then it's going to be giving you false readings. You always need to read from the bottom of the meniscus with your eye level at that point. So the meniscus is the little curved bit that you get with the liquid in a tube. So you've got to get your eye level with the bottom and then read the numbers from there. You should always record the 2 decimal places in a titration. So if it's on a line, then it's a 0 as your second decimal place. If it's between 2 lines, then we record the second decimal place as a 5. When you're carrying out the titration, you should always swirl the flask in order to mix the contents. And then as you approach the end point, we add it a drop at a time. You don't just turn the tap on and then have a chat with your friends and then look back and think, oh, it's gone, and turn it off. That would be the worst titration you could do. When we've actually done that, and still just for the higher folks, we need to know how to carry out a titration calculation. I would guess this is coming up tomorrow, I'm afraid. So what we actually have here is when we've done a titration, we know a few things. We know which 2 reactants we used. We know the volume and concentration of one of those reactants and the volume of the other reactant. Now we can use that information to calculate an unknown concentration. And we do that by using the equation, amount in moles is concentration times the volume. Now, key thing here, volume is in decimeters cubed. So where they're going to give it to you in centimeters cubed, we need to obviously convert to decimeters first of all. then I'd suggest the first thing that you do if you see a titration calculation question is draw out your little triangle to help you out. So this is the triangle that we need. So N is your amount in moles, C is your concentration, and V is your volume. If you've got that, then you're just going to be using that equation, rearranging it slightly differently a few times over to get your final actual concentration. So key steps that we're going to go through in order to actually do a titration calculation. Step 1, convert all the volumes to decimeters cubed by dividing by 1,000. Step 2, calculate the amount of the reactant you know, because we've got volume and concentration. So if we've got concentration and volume, we can calculate the amount in moles. Then we write out our balanced symbol equation, and from that we can work out the ratio, so we know the amount of the other reactant in moles. That then gives us the amount in moles and the volume. We can calculate the unknown concentration because we will have the amount in moles and our volume to allow us to calculate that. So that's all we need to do with these. As daunting as they look, because it's not just a simple one-step calculation, there's little bits to do, then it's not as bad as you think. Even if you can't remember how to get to the end, then at least do the first bit. So if you remember that when they've given you the concentration and the volume of one, multiply them, get the amount in moles, you've got some of the marks rather than just flipping the page and thinking, I can't do that. So always have a go and see how far you actually get with it. Just set it out nice and clearly, show you're working. Do not just write down a random sort of number at the end, because even if your random number was right on your calculator and you copied down just one tiny thing wrong, you've got nothing. If you've showed the working, you've got all but that last mark for the actual answer itself. Next thing for the higher tier, we need to know about the gas calculations. So 1 mole of any substance in the gas state occupies the same volume at the same temperature and pressure, and that is the molar volume. So at room temperature and pressure, which they'll summarize down to RTP, then it's 24 decimeters cubed per mole. So another calculation for us to remember here, so the volume in decimeters cubed is the amount in moles times 24. So if it asks you how much, what volume 5 moles of hydrogen would occupy, you just do 5 times 24, it gives you your volume there. So it really doesn't matter what gas it is, it's the amount in moles times 24. That's all of C5 done. Last thing we need to do now is C6 for the separate sciences. First thing here is fertilizers. So hopefully we know that plants need certain elements which are called the essential elements for growth. Nitrogen, phosphorus, potassium. So nitrogen, if we don't have enough of it, then our plants will have yellow leaves with very poor growth. Phosphorus leads to poor root growth and discoloured leaves. And potassium is poor fruit growth and discoloured leaves. The reason we actually use fertilizers is because we're replacing the elements that the plants use as they grow. Now, we need to have a fertilizer that's soluble in water because it has to dissolve in order to be absorbed through the roots of the plant. So the ones we're going to use, in terms of our nitrogen, it will be nitrate ions or ammonium ions. For phosphorus, it's phosphate ions, and potassium, potassium ions. So they're all soluble, they'll dissolve in water and then taken up by the plant's roots. With the fertilizers, we have what's called NPK fertilizers. N for nitrogen, P for phosphorus, K for potassium. And they come in different ratios depending on what you need it to cover. So if they were to ask you which fertilizer you'd use for a plant that's got yellow leaves, then you're looking for one with the maximum amount of nitrogen. So just look at the actual chemical formula, find the one with the most atoms of nitrogen in it, that's your pick. In terms of the making of fertilizers, then this goes on to our next process, which is the Haber process. So the Haber process is used to make ammonia from nitrogen and hydrogen in a reversible reaction. So raw materials that we've got here are air, natural gas, and steam. So we get nitrogen from the fractional distillation of liquefied air, and hydrogen by reacting natural gas with steam. And what we will actually do here is, once we've actually made things like our ammonia in the Haber process, then we can use that, react it with an acid to make our salt, which we will use in our fertilizer. Now, they have asked you about making these fertilizers before, and you've got two different ways they can phrase it. They can give you the name of the salt and ask you what acid and alkali were used, or they can tell you the acid and the alkali, and you've got to name the salt. So again, this goes back to our rules about look at the acid, it gives you the ending. So hydrochloric acid is a chloride, sulfuric a sulfate, nitric a nitrate, and phosphoric a phosphate. So what we find there, you've got your ending. So if they tell you the salt is something like potassium sulfate, then we know it must be sulfuric acid. So that gives you one of your reactants. And then if we're looking for what else it could be, if it was potassium sulfate, we made potassium something as an alkali, so we can go with potassium hydroxide or oxide. So just stick oxide or hydroxide after the name of the metal and you'll be fine. So making our fertilizers, it's a titration, which we've already gone through. Hence why titration is quite likely to come up as an assessed practical, because it pops up in a few different places here. Now, we've got two processes that we use to make chemicals in industry: batch and continuous. So bulk chemicals are the ones we need in large amounts, and we make them through continuous process. And specialty chemicals, like the pharmaceuticals, are needed in small amounts. So these are the ones that we make by batch process. They could very well ask you to pick whether it's batch or continuous as the process that we should use to make a certain chemical. Or they could ask you about, give two other reasons why we should use process X. So you need to be able to compare them. So in terms of the rate of production, in batch process it's low, but continuous is high. The cost of the equipment in batch is low, whereas it's high in continuous. We need lots of workers for batch process and only a very small in continuous. There's frequent shutdown periods in batch process, but rare shutdown periods for our continuous. And it's very easy to automate the continuous process, but not very easy to automate batch. So you can just look and see which one of these is going to apply to the scenario they've given me, put that in. In terms of our Haber process, hopefully this diagram looks familiar to you. So we start off with our nitrogen and hydrogen that's pumped in here, and we put them under high pressure. It's then pushed through into the reaction vessel, which has got these beds of an iron catalyst, and this is at 450 Celsius. And then it comes down to a cooling area where we then have our ammonia collecting at the bottom, and any unreacted gases, back they go. So what we can see there is the basis of our Haber process. Now, we need to know the three conditions to carry this out: 450 degrees Celsius temperature, 200 atmospheres of pressure, and an iron catalyst. Now, the reason that we've got these for the higher tier is because this is a reversible reaction. So what we need to do here is go back to what we've already looked at earlier on about why we pick temperatures, pressures, etc. in a reversible reaction. So if we think about temperature, first of all, the forward reaction is exothermic, backward reaction is endothermic. We know increasing the temperature moves the equilibrium position to the left, and that means it would decrease the yield of ammonia. That wouldn't be great. So what we find here is the lower the temperature, the higher the yield of ammonia. But the higher the temperature, the faster the rate of reaction. So we use 450 because it's a compromise between rate and yield. Second one, the pressure. This is where we look at the number of moles of gas on the left and the right. So if we increase the pressure, our equilibrium position moves to the right and yield increases because we've got fewer moles of gas on the right. Again, we're using a compromise here though. We don't just keep upping the pressure endlessly. We use 200 atmospheres for the simple fact that it gives us a high yield without those extravagant costs of equipment that has to withstand vast pressures. And we also eliminate the risks of those high pressures as well. The other thing that we will do in order to obviously maximize our actual profit is to make sure that any of those gases that are unreacted at the end are recycled back in. So that's why we've got the condenser, because the ammonia will turn to a liquid, allow us to collect that, whereas any of the nitrogen and hydrogen that's unreacted, straight back in, so it's not wasted. One of the things they could give you is this delightful graph. Now, obviously, if you like graphs, that's pretty straightforward to read. We've got 4 lines on there for the 4 different temperatures. We've got our yield on our y-axis and pressure on the x-axis. So you can read those off, identify which is the best temperature, which is the best pressure, and we can apply our knowledge that we've just gone through to explain why. If you hate graphs, just learn the reasons. So we know that the yield is going to increase when we've got a lower temperature. And we know that the yield increases with a higher pressure. So if you hate reading graphs like that, memorize the patterns. You don't really need to read it. Next up for the higher tier is the contact process. So this is the process we use to make sulfuric acid. 3 raw materials: sulfur, air, and water. So we've got a 3-stage reaction taking place here. Stage 1 is burning sulfur in air to produce sulfur dioxide. Stage 2, sulfur dioxide and oxygen reacting to make sulfur trioxide, which is SO3. And to do this, because it's a reversible reaction, we use 2 atmospheres, 450 degrees Celsius, and a vanadium oxide catalyst. And then stage 3, sulfur trioxide is converted to sulfuric acid by adding water. One thing to note though, we don't just throw water on sulfur trioxide. That wouldn't end well, because what we find is that is a very exothermic reaction. So if we just literally threw water on our sulfur trioxide, we'd have a very dangerous acidic mist created. That's not good. So instead, we break it into 2 steps. Sulfur trioxide is passed through concentrated sulfuric acid to make oleum, and then the oleum is added to water to make a large volume of concentrated sulfuric acid. What we find in terms of our reversible reaction in stage 2, the reason we pick those conditions is because the equilibrium position is far to the right already. So high pressures aren't needed. We're not going to waste our money on that. We only use 2 atmospheres to move the gases through the converter. The forward reaction is exothermic, which means backward is endo, and therefore a high equilibrium yield is favoured by low temperatures. But again, we pick the compromise between yield and rate. So vanadium oxide is another reason for our choice of temperature, because the vanadium oxide catalyst only works above 380 Celsius. Still, for the higher tier, we need to know how to make ethanol. So we've got 2 different ways we can do this. We can use renewable raw materials first of all, and these are the ones that can be replaced because they're not going to run out. So as soon as you use it, you can then grow some more trees or more plants. What we find is that ethanol is made in a fermentation reaction. So yeast contain enzymes that convert glucose into carbon dioxide and ethanol, and the glucose that we've got here comes from a plant. So all we're doing there is changing glucose into carbon dioxide and ethanol. If the temperature is too low in this case, then our yeast cells become inactive. It's enzymes, going back to our biology knowledge here. If the temperature is too high, then our enzymes become denatured, and that means the active site has changed shape, it won't fit the substrate, and therefore it won't work. Fermentation then we carry out at about 35 degrees Celsius as a result. The other way we can do this is by using non-renewable raw materials, and these ones are used faster than they can be replaced, so they will eventually run out. And the one we're using here is ethene, which comes from crude oil. So ethene can be hydrated to make ethanol. So ethene plus water will make ethanol, and it's reversible. So remember, reversible reaction sign. We'll have 3 key conditions here: 300 degrees Celsius, 60 atmospheres of pressure, and a phosphoric acid catalyst. Again, if you're looking at these 2 processes, you need to be able to weigh up the pros and cons of each. So make sure you do know the different kind of features of them and can compare fermentation to hydration. In terms of higher and foundation for the GCSE chemistry now, we need to know about alloys. So an alloy is a mixture of two or more elements where at least one is a metal. We've started the single science stuff quite some time ago. We're now approximately halfway through C6 for the single sciences. So you might want to scroll back in the video a bit later on. We need to know about 5 alloys. Steel, which main metal is iron, and we use that for buildings. Solder is tin and copper, and we use it to join electrical components. Brass, copper and zinc, used in musical instruments and coins. Bronze is copper and tin, which we use in things like bells and ship propellers as the really well-known examples they like to give us. And duralumin, which is aluminium and copper, which we use in aircraft parts. What we actually find is we need to justify why we use these things as an alloy rather than just the actual metals they're made of on their own. So if we think about solder, first of all, then it melts at 227 degrees Celsius, which is actually quite low. And that means it's not going to damage electrical components when it joins them together. It also turns to a liquid and will flow into gaps and fill them before it reverts to its solid state. And it's got the very useful bit here of conducting electricity. If we're thinking about the difference between brass and pure copper, if we had pure copper, then the atoms are all the same size, therefore they slide over each other really easily. So that means it changes its shape quite easily and isn't as strong. If we use brass, then zinc and copper atoms are different sizes, so it's going to be more difficult for the copper atoms to slide over each other. So that's why we use it, because it gives it additional strength there. Bronze is also corrosion resistant, and that means it's going to be better to use in things like propellers, which are submerged in the water. Which leads us very nicely on to our next bit on corrosion. And again, this could be a practical they throw in. Hopefully you did it in class where you had test tubes and some nails with some with water, some with random little chemical and so on that you left probably sitting on the side in your science lab for months on end, and they might still be there now if it's anything like my classroom. And what we did there was we were looking to see the rate at which it was rusting. Now, corrosion is the reaction of a metal with substances in the surroundings. Some metals are more prone to corrosion than others. So the only metals that don't corrode are the very unreactive ones, things like gold and platinum, hence the ones we use in jewellery, really. If we're talking about rust, that's hydrated iron oxide, and rusting is a redox reaction. So iron plus oxygen plus water makes hydrated iron 3 oxide. And the big downside of rust is that as the hydrated iron oxide flakes off the surface, then it's going to expose new iron underneath, which will then react with the water and the oxygen in the surroundings. So because we need oxygen and water to carry out this process of rusting, in any of your test tubes that have either no water or no oxygen, we won't get rusting. It's the one that's got air and water present that will rust. So just look for that in terms of a pattern. If they ask you how we can reduce corrosion, pretty obvious things here. A little bit of common sense, you should be fine. You can paint them, we can coat them with oil, grease or plastic, we can plate it with zinc or plate it with tin. So any of those are ways to prevent corrosion. For the higher tier folks, we need to know what happens during rusting in terms of our little half equation. So Fe, which is our atom, will become Fe3 plus 3E minus, our electrons. The more reactive our metal, the more easily it loses electrons, and therefore the more readily it's oxidized. Just remember that little pattern there. Back for foundation and higher folks now, we need to know about a process called sacrificial protection. Now, when we're talking about sacrificial protection, it's kind of as the name suggests, we're using a more reactive metal than the one we're trying to protect. So the more reactive metal is throwing itself on its sword, if you like, and giving up its existence for the good of the less reactive metal. So we would do things like attach these blocks of magnesium onto a ship's hull. The magnesium will be corroding before the iron does. If we think about metal plating, then this involves a metal being plated onto the actual surface of the metal to be protected. That's just going to prevent air and water from reaching the actual metal we're protecting, and that means it won't corrode. If we think about galvanizing, that's where we dip our metal into molten zinc. So that's quite a common thing with nails and things like this. Dipped into molten zinc, and again, protects it. If we think about tin plating, this one involves electroplating steel with tin. Now, this is what we do with food cans because they're tin plated on the inside. But tin is less reactive than iron. So if there's any damage to the actual surface of the actual plating, then it's going to accelerate the corrosion, because obviously the iron will be actually carrying out sacrificial protection of its plating. Next thing we need to come on to are the different materials that we can use. And one type of material we need to know about are ceramic materials. So brick, china, porcelain, glass. The ceramics all have very similar properties: high melting points, hard, stiff, brittle, poor conductors of heat, poor conductors of electricity. Now, what these ceramics actually are hard, non-metallic materials. So they contain metals and non-metals which have been combined to form these giant ionic lattices or giant covalent structures, depending on what they're made from. The ceramics themselves are mostly made of oxides, which means they're unreactive at this point. So in terms of how we make glass, then sand is melted and allowed to cool. If we want to make brick, we heat clay to higher temperatures, and then it's going to turn into the bricks we built our houses out of. If we want to make china and porcelain, then we heat clay to high temperatures, coat it in a glaze, and then we reheat it. Now, when we actually melt and cool sand, then it forms this giant irregular structure without crystals. When we heat clay to high temperatures, tiny crystals form, which are joined together by glass. The next kind of material that we can have are composite materials. Yeah, the wolf is my Alaska Malamute in the background. Don't worry, I'm not about to be devoured by some random creature. So composite materials are made from two or more materials with different properties being combined together. And the idea of this is that the composite material then has properties that are different from those of the materials it contains. Now, many of these we make by embedding fibers in a resin, things like fiberglass, for example. And we will then also use the glass fibers there embedded in the resin to make it. So things like canoes and kayaks, for example, are fiberglass. So we've got these very small glass fibers, we embed them in a resin, and it makes it really strong, but it's lightweight, so it's perfect for things like that. Carbon fiber used in our sporting equipment, also used in things like aircraft parts and racing cars. Again, we've got these tiny fibers of carbon there that we're using. Next thing is thinking about concrete. Now, when we come to doing our buildings, then we will actually have concrete, which is a composite made from aggregate, which are basically little bits of stone, sand, and cement. When we add water to it, chemical reactions occur that bind everything together. Now, concrete itself has high compressive strength, so it's very strong when you push down on it, and therefore brilliant for foundations of buildings. But it has a low tensile strength. So if we were just to make a concrete beam, then when we place a load on it, it's quite likely to crack. So that's not ideal if you're building your floors out of concrete. You don't really want that cracking. If we think about steel, that's got a very high tensile strength. So what we do is we mix the steel and the concrete to make steel reinforced concrete. And as a result, it's got high compressive and high tensile strength. Next thing we need to come on to are the alkanes. So we're going to have a look at some organic chemistry now. So alkanes are a type of hydrocarbon. If they ask you for the definition of a hydrocarbon, which used to be a good favourite for them for 2 marks, then we need to write down it's a compound made from hydrogen and carbon only. That word only was always worth 1 of the 2 marks. Alkanes are an example of a hydrocarbon, and they form a homologous series because they've got certain features in common. So they've got the same general formula and they're saturated, which means they've only got single bonds between the atoms. You could potentially be asked to name them. So the prefix, the first part of the name, comes from the number of carbon atoms. So 1 is meth, 2 eth, 3 prop, 4 but, 5 pent, 6 hex. Make sure you know those bits because that's going to be used in all of these different organic molecules. The last part of the name, so the ending for it, if it's an alkane, is just ANE. So nice and easy. If we had something that had 3 carbon atoms and only single bonds, then it would be propane because prop means 3 carbons, ane, single bonds. The general formula for our alkanes is CnH2n plus 2. So make sure you learn those general formulas. If we've got an alkane and we burn it, 2 types of combustion, complete and incomplete. So complete combustion leads to complete oxidation of our hydrocarbon into carbon dioxide and water. So the hydrocarbon plus oxygen makes carbon dioxide and water. Simple. Incomplete combustion is when we don't have enough oxygen present to completely oxidize it. So what we actually find here is that we're going to make carbon, carbon monoxide, and water. When we come on to our second type of organic chemical, it's alkenes. Okay, the subtle difference is an E instead of an A. So they're still hydrocarbons made of carbon and hydrogen only. They still form a homologous series because they've got the same general formula, and these all are unsaturated, which means they contain at least 1 double bond. So unsaturated, at least 1 double bond, saturated, only single bonds. General formula for our alkenes is CnH2n. Now, what we'll find here is if we carry out combustion with an alkene or an alkane, products are the same. So it can be complete or incomplete. Same process, because they're both just made of carbon and hydrogen. Key thing to remember about our alkenes is the functional group. So the functional group of an alkene is the C double bond C. So that's its functional group. When we talk about a functional group, it's atoms, groups of atoms, or types of bond in a molecule that are responsible for the characteristic reactions of the substance. Hence the functional group of alkenes being the C double bond C. If we talk about an addition reaction, then that's where groups of atoms or atoms themselves combine with a molecule to form a larger one with no other product. And a good example of this are the addition polymers, which we're coming on to a bit later on. If you've got a chemical, you need to know, is this an alkane or an alkene? All we need to do is add bromine water to it. So when you add bromine water, then it will go from orange-brown to colourless if it's an alkene. So the ethene plus bromine makes dibromoethane because it's just an addition reaction. We're adding the bromine onto our alkene. Alkanes, we can't add bromine. There's already all single bonds. There's nothing to add the bromine to. So it stays as the orange-brown colour. Third organic chemical are the alcohols. So these have the functional group of a hydroxyl group, so OH. Their names all end in OL, so alcohols, and they have the general formula CnH2n plus 1 OH. Now, what we find is if we burn alcohols in oxygen, we produce carbon dioxide and water in complete combustion. In incomplete combustion, water vapour, carbon monoxide, and carbon are produced. One other reaction that we can do with our alcohols is we can oxidize them to form carboxylic acids. Which brings us to our fourth one, the carboxylic acids. Now, functional group for carboxylic acids is, as my lot like to tell me, COOH, so COOH. Now, that is the carboxyl group. The names of all our carboxylic acids will end in anoic acid, so ethanoic acid, methanoic acid, etc. And they've got the general formula CnH2n plus 1 COOH. Do be careful when you're working this out, because if they give this to you, it's one that you could easily throw away the mark on, because one of the carbons is actually in the functional group. So go careful not to add an extra carbon in there. When we've got our carboxylic acids, then we can form them when the alcohols react with an oxidizing agent, such as potassium manganate. Now, When we do this, what we find is the manganate ions, which are purple in their first instance, are reduced to manganese ions, which are pink. So that means you can see that colour change to know this has taken place. And when acidified potassium manganate oxidizes ethanol, it makes the ethanoic acid. We do need to remember that carboxylic acids are weak acids. So that means they're going to have the same reactions as acids because they are acids. So if we react a carboxylic acid with a metal, we make salt and hydrogen. Carboxylic acid with an alkali or a base, it's salt and water. Carboxylic acid with a carbonate, salt water and carbon dioxide. Go back to those same general formulas and equations that we learned when we did just metals and acids and so forth. One thing to remember about the salts we're making though, they will all have the ending OATE, so O8. So ethanoic acid plus sodium carbonate would make sodium ethanoate plus water plus carbon dioxide. The next little section is about our polymers. So we need to know a few different types of polymers here. First one, the addition polymers. One of the key ones we've looked at are plastics. Now, polymers are made from many monomer molecules being joined together, and the monomer molecules are usually alkenes. Lovely mouthful there, but you get the idea. Now, when we're actually coming to how we name a polymer, then if we had the name of the monomer as ethene, then to make the polymer, all you need to do, write the word poly in front and stick some brackets. If they gave you the polymer and wanted the name of the monomer, all we do, lose the brackets, lose the word poly, and there it is. So that's the easiest thing in the world if they ask you to name a polymer. Now, what we find is that we will see this addition polymer. Let me try that again. We get addition polymers undergoing an addition reaction as they join together. So the reason that they can do this and the reason that we have our alkenes as the monomers that are going to join to make our addition polymer is because of that carbon double bond carbon bond. So what we actually find is the double bond is broken, and that means they can then join to other alkene monomers. So when we look and see how the displayed formula occurs, if we've got one like this, so that is our monomer, then what we need to do to draw the displayed formula for the polymer, get rid of the double bond, put square brackets around it, little N in the bottom corner, and the bonds just coming out the side from the carbon there. So that's how you just change it. If they gave you this one and they wanted you to draw the monomer, then it's the reverse. Take away the square brackets and the N, and then just stick a double bond back in the middle. So it's quite easy to draw the displayed formulas for those. Just remember that little thing. That's quite a simple way to pick up some marks there. In order to carry out addition polymerization, we do need high pressure and a catalyst though. Next type of polymers, the biological polymers, and I promise we are almost there now, folks. DNA is a polymer made of monomers called nucleotides. Each nucleotide consists of a phosphate group, deoxyribose sugar, and a base. And hopefully you know the block diagram for that. 4 bases, adenine, thymine, cytosine, and guanine. And we've got hydrogen bonds that form between the bases on the 2 strands of DNA to hold the double helix shape together. Other biological polymers, we've got proteins, because they're polymers made from the monomer amino acid. We've got 20 amino acids that occur naturally in our body, and each has a reactive functional group at the end that allows them to join end to end. We've also got carbohydrates, which are made from compounds of carbon, hydrogen, and oxygen. They're monomers of simple sugars, which again, we can join to make a complex carbohydrate there, like glucose being joined to make starch, for example. For those of you doing the higher tier, you need to know about condensation polymers. By the way, if someone fakes an exam, you don't get your forecast grades at all. The absolute best case scenario for a special consideration form is that you might get 5% if you're lucky added onto your score. So maybe just do your best. In a condensation reaction, then two molecules react together to form one larger molecule and one smaller molecule, which is often water, hence condensation. So what we will find here is the condensation polymers are formed by condensation reactions. They don't require a catalyst, and they often occur at room temperature and pressure. Key thing though is that the monomers for the condensation reaction will need two functional groups. So this is things like our proteins. So amino acids have two functional groups. They've got their amino group and a carboxyl group, and the monomers are joined by an amide group, which is CONH. To give you a couple of examples here of the condensation polymers, we've got polyester and polyamide. So polyester is made from a carboxylic acid with two carboxyl groups and an alcohol with two hydroxyl groups. So they're able to form many ester groups when they're formed, hence polyester, many esters. These are what we'll use in lots of things like the drinks bottles that you will take into the exams and various items of clothing. Polyamide is made from carboxylic acid with two carboxyl groups and an amine with two amino groups, and they form many amide groups, hence polyamide, many amide. And this is a good example with nylon, which we use in clothing, carpets, and all that malarkey. The very last thing that we need to do, which is for foundation and higher, is looking at how we produce electricity using chemistry. So looking at fuel cells and chemical cells. So chemical cells have an exothermic reaction within the cell that develops that potential difference between the two ends of it. So when we connect that cell into a circuit, current flows through the cell and the circuit components. So that's what we have with our standard batteries. We can also use a fuel cell, which produces electricity through a chemical reaction between a fuel and oxygen, but without combustion. Now, this is very useful on things like the space shuttle and so forth, because burning stuff in space, pretty bad idea. We still need electricity, and so we use fuel cells for this. And what happens is hydrogen reacts with oxygen in an exothermic reaction to produce water vapor. And the hydrogen-oxygen fuel cells use that reaction, but it's been separated into two reactions, one on each side of the actual cell itself. So your cell looks something like this. So we've got the two sides there, which are separated by this central section, the proton exchange membrane. So the hydrogen fuel comes in on this side, and then we've got oxygen coming in on the opposite side, and we can see in the middle, hydrogen ions are going from here across there through the proton exchange membrane. The electrons go up through an external circuit and then are fed back in on the other side. Very brief overview. The first thing that's going to happen is that hydrogen molecules lose electrons to become hydrogen ions. So our two hydrogen molecules, H2, will form 4 hydrogen ions, H+, and 4 electrons, E-. The hydrogen ions pass through the proton exchange membrane to the other side of our fuel cell, and the electrons go through that external circuit to the other side, as we saw. Then the hydrogen ions combine with the oxygen and the electrons to make water vapor on the other side, which means we've got 4H plus O2 plus 4E- gives us 2 H2O, and it's vapor, therefore our state symbol is a G. In terms of advantages of our fuel cells, they're lightweight, they're compact, there's no moving parts, there's no combustion. The only waste product is water, so we've not got carbon dioxide emissions, and we've got a plentiful supply of hydrogen. There are some disadvantages though. It's currently mostly our hydrogen is made through the use of fossil fuels. Now, we also have poisonous catalysts in fuel cells that we then have to safely dispose of at the end of its life. So what we find is if we're using a catalyst that's poisonous in something, that's generally not good, because we've got to find a safe method for its disposal once that fuel cell has come to the end of its existence. Right, we are now done. It's taken us 2 hours, but we got there in the end. So that is a brief summary on everything that could, in theory, potentially come up in your exam tomorrow. So what I'd suggest you do is go over any of the bits you're really not sure on tonight. Make sure that you are reading the questions carefully tomorrow, because they do give you a fair amount of information in the question itself, and sometimes just blatantly the answer. And also look at the number of marks it's worth, so you're not throwing away things there. But most importantly, don't panic. Make sure you don't stay up all night tonight, because that's the worst thing you could actually do. Make sure you get some sleep, because that's going to mean your brains are actually working tomorrow. And for those of you who are still looking forward to the physics on Friday, we will have another live stream on Thursday night, again 6:30 for our start time, to go through all of the last physics units. Good luck tomorrow, everyone, and I hope that you will all do well and the paper will be nice to us all.